Okay, so we're here for the study session, if you will, for our test 2, and also to answer questions about homework 3. And I'd like to start off today by going over some things, especially from chapter 7. Even if they were things that were covered in lecture, it's kind of good to repeat certain things, and maybe I get a chance face-to-face to emphasize something clearer than what we do in the videos. So I'm going to start with some material, open up the floor to questions you might have about things, preparing for the exam. And then I'll do more material after we run out of questions, provided we have time. That's what I've got in mind. Okay? The first thing I'm going to start off with is, in Chapter 7, one of the main things we started with is point-wise convergence for sequence of functions. So I'm going to write down that definition. So here it is on the board. And as a definition, we say a sequence. And really this, a sequence of functions. And we denote them by f sub n, as n runs from 1 to infinity. This sequence of functions defined on a set n is said to converge pointwise to a function f on E if I'm going to say it this way, if for each x ending and each epsilon greater than 0, there exists a natural number n sub x comma e. So the n depends on x and e, such that for all n bigger than or equal to this big N sub x comma e, f sub n of x minus f of x will be less than epsilon. Okay. Now, that's what I've written here today. That isn't perfectly coinciding with what was written in your notes, okay? And what's written in your notes is equivalent to that, okay? What I'm doing here is giving kind of a little bit more of an emphasis on the natural number. Well, let me give everybody a second. We're going to take it. In the notes, what does it mean for this sequence of functions to converge pointwise to f? It means for each of the x's, f sub n of x converges to f of x for each of the x. Okay? So you give me an x, fix that x, then I can show that sequence of numbers, complex numbers. We're talking about the complex value functions in general here. That sequence, f sub n of x. Okay? So you fix x, x sub, let's call it x sub naught to make it a solid x. Okay, fix x. F sub 1 of x sub naught, f sub 2 of x sub naught, f sub 3 of x sub naught, f sub 4 of x sub naught, and so on. That's a sequence of numbers that converges to something. What it converges to, we call f of x sub naught. Is that all right? And we do that for each x. Okay? And that's what it means for that sequence to converge pointwise. Now, look, what does it mean for that sequence of numbers to converge to some number, f of x? Well, that means that there exists this n, given epsilon, there exists this n, this natural number, and the n can depend on epsilon, such that when you push beyond that n, the terms f sub n of x, their distance from f of x, that's what this norm means, will be less than the positive number that you gave me. So I can make, for each x, I can make the f sub n of x be arbitrarily close to f of x. That's what I can do. Let's look at an example. Okay, consider the sequence of functions f of n, and learn from one to where f sub n of x is defined to be x to the n, defined on, and this is something I think I did in the lecture, in the video lecture, defined on 0 to 1. That's what I got. Then, the f sub n's converge pointwise to this function, f, it's equal to 0 if x is an element from 0 up to 1, but not including 1, and 1 if x is equal to 1. Okay, I know that this is not on videotape, so let me move it. Okay, I'm going to get out of the way. We're essentially videotaping because two people are next.
Thank you. Excuse me. Oh, gee.
Okay. Now, I want to kind of go through this today, if you don't mind. I know we all want to be doing other things, but I'm going to take my time and we're going to go through it, see how long it takes us. But I think the concern here is that let's make sure we have some basics set today and make sure of that so that when we're preparing a little bit more focusedly for that test, it's going to be, it seems like forever back on Monday. Is that right?
Yes.
Okay. Ruthie, again,
Yes. I didn't email you, but I am also.
okay, that's great. That we get some of these ideas down. I think that that's good. It gives us a little bit more time. Okay. Look, I'd like to start drawing these f sub n of x's, and I did before for the video lectures. Here's what they look like. Look, we're defining from 0 to 1. And if you say, what's f sub 1 of x? F sub 1 of x. Look, let's make sure we understand what we're talking about. F sub 1 of x. It's just x to the first. X to the first, y equal to x. Y equal to x is nothing. My grandmother could graph y to the x, and she doesn't even speak English. Okay? Y to the x, nothing. That's this guy. It's that straight line. Okay? What's f sub 2? It's x squared. All right, it's this guy, but we're just talking about from 0 to 1, so we're talking about this. It's got a little curve. And then what's the next one? It's x cubed. That looks like this. And they keep on going. Is that all right? Okay, and so forth. Okay, now look. What happens is, I want to prove this. I want to prove this claim that I have here to the left. Beautiful, just fantastic. So how do I prove this? Well, what I'm going to do is I'm going to take any x that's in 0 to 1, that's my e. Take any x in 0 to 1, and show that f sub n of that particular x goes to 0 if the x is in between 0 and 1, not equal to 1. Okay, I want to show that. And then if it's equal to 1, I want to show that it converges to 1. Okay, well, let's let x be an element of 0 to 1, like this. We want to prove, for this fixed x, we want to prove f sub n of x has a sequence of numbers converges to 0 in this case, okay? In this case. Okay? Even though I don't have the camera moving with me over here, I never hold it. Let's see what happens. But when I look at this guy here, and I fix some x, okay? And you look at f sub 1, and then you look at f sub 2, and then you look at f sub 3 of that x, and f sub 4 of that x. What are they going towards? 0. I mean, that's the idea. Is that okay? Okay, so I'm glad. Sorry if I'm going too slow. Okay. Okay. All right. How do I show this? Well, here's what we do. We let epsilon be greater than 0 be given. What do I want to show? How do I show the sequence of numbers converges to 0? The way we do that, we need a natural number n such that for all little n bigger than or equal to that big N, the distance between f sub n of x, that's a number, and 0 will be less than this epsilon. I can make the f sub n of x's be arbitrarily close to 0, okay, for all n's far enough along in the sequence. That's what's being said. Okay, so that's what I want to happen. That is, so let's kind of break down what it is we want to show. That is, we want the absolute value. Well, what's f of n of x? Well, that's defined to be x to the n minus 0 to be less than x. That's what I want. Because f sub n of x is x to the n. Okay? All right. So we want x sub n minus 0 is just x sub n inside absolute values to be less than epsilon. And here, because we're talking about real numbers, we do mean absolute values. That's what I mean. Okay, well look, the x sub n's are positive numbers in this case. Well, non-negative numbers, could be 0. And so their absolute values are themselves. Is that okay? So we want x sub n to be less than epsilon. I haven't got this. I want that. And what do I want? When do I want it? I want it for all n's bigger than some particular spot. I want this to happen. Okay? Okay. Well, the object of the game here is to solve for n. Okay? Now look, x is a fixed number. We're teachers in here, and I think some of this subject that I'm about to use, some of you teach. This will come up in Shawnee State pre-calculus. This is really an exponential inequality. But let's just say it was an equation for a second. How do you solve exponential inequalities? Anybody got an idea? Well, laws. That's exactly what I'm going to use. So what I'm thinking is that we want ln of x to the n to be less than ln of epsilon. That means I pull the n out front by properties of logarithm. We want n times ln of x to be less than ln of epsilon. Now, x is some number in between 0 and 1. And I guess I should be a little clear, so I think I'm in trouble for a second in terms of proof. If x is equal to 0, I can't take the log of it. Does that make sense? So what we're doing really, we're saying if x is equal to 0, it's clear f sub n, so I'm kind of an aside, f sub n of x. And when x is 0, what's f sub n of x? Well, it's 0 to the n. And that means it's always 0. So when x is equal to 0, f sub n always is 0. And so a sequence of constant functions is going to converge to that constant, if we're good with that. Okay? So I guess I'm kind of thinking x is going to be between 0 and 1. That's open. I'm changing. When it's 0, we got it. Okay? When it's 1, we got it. Because f sub n of 1 every time is going to be 1 to the n, which is always 1. And so that's going to converge to 1. And that's what we've already said here. Is that okay? Okay, so I'm kind of just doing those in the air. Here, I divide both sides by ln of x. ln of b divided by ln of x. Now wait. When x is between 0 and 1, let me graph right here. You guys remember what y equal to ln of x looks like? It looks like this. Here's 1. This is this graph. That's what it looks like. Okay? When you're dividing by ln of something, when that something's in between 0 and 1, what kind of number is ln of that something? What'd you say? It's negative. Ruth, you said the right thing. And when I divide an inequality by a negative, I have to switch the direction. Is that all right? Okay, so that's what I got. If I'm going too slow, I'm sorry. Okay? But that's what we got. So, how do I know I can get some natural number bigger than ln of e divided by ln of this particular x? Well, this was probably negative too. First of all, if it was negative, definitely any n will work. But if this ln of e, if e is really small, ln of it's going to be, what kind of number? Negative. And so we take a negative divided by negative, that could be positive. Is that okay? Okay. So how do I know I can get an n if it was positive? How do I know I can get an n bigger than it? It's been a little while, I guess. There's a big fact. The set of natural numbers is
1.
How do I know I can get a natural number bigger than ln of epsilon over ln of x? Because the set of natural numbers are not bounded above. Okay, I'm going to stop there. They keep going. Is that all right with everybody? And so I know there's a natural number bigger than this guy. Is that all right? That's what I think it's called the Archimedean property. Did we call it that? Okay.
You call it whatever you want.
All right.
It's called the Lord property.
Okay. By the Archimedean property. But, even if we don't know the name, Ruby said the right thing. Okay, she said they're going forever. So we can get bigger than any number. Is that okay? They're going forever beyond anything. There exists an n such that there exists an n, there exists a natural number. Big N, such that big N is bigger than this ln of epsilon over ln of x. So for all n bigger than or equal to this big N, we have exactly what we want. It will translate into f sub n of x minus 0 being less than epsilon. And this is true for the x's in between 0 and 1. And we've already handled when x is 0. When x is 1, what will happen? I just did it kind of in the air. Is that okay? We are with what I said. Okay, let me give you a little bit more. Okay, so as an example, and this is true, as an example, if x were equal to 0.9, I'm sorry, Chris. I say that to you because of the comment you made about me coughing. How bad it is. That your wife has to say, oh my God. And I told you, I annoy enough people. I'm supposed to annoy someone else. Okay, 0.9 is way over here. Okay. And look, most of those functions are going to be really close to 1. They get, they're kind of going up. So how many n's, how big of an n do we have to have that will raise 0.9 to a power if we let equal to 0.001 to get 0.001 units of what? What do I say it's going towards? 0, that's right. So look, if you want to be within 0.001 units of 0, you want to be right within that band of 0. You see where I'm putting? Here's 0. Wait a minute, look at it. Here's 0, the x-axis. And I'm saying this is 0.001. And you can go below 0.001, but none of the functions are going below. I want to be within that band. Is that okay? For just 0.9, I want to make sure you get within this band. These guys. Okay? How far along do I have to go in terms of the sequence? Well, this work here says So n has to be greater than ln of 0.01 over ln of 0.9. You can take a calculator, okay? That's a number. And that says n has to be greater than or equal to 66. So what I'm saying is to force F sub n of 0.9 to be within 0.001 units of 0, you have to go to the 66th function in this sequence. And then from then on, all the functions of that sequence evaluated at 0.9 will be within 0.001 units of 0. Does that make sense? What if I took 0.99 and wanted to be within 0.01 units? Could I use the same n? No. I got to push further along. Is that okay with everybody? Okay. And you know, if I hadn't used 0.99, if I just used a half, I wouldn't have to push as far as 0.65. 66. I wouldn't have to push that far if I just used a half. It's going to get down to below 0.01 a lot sooner. Okay?
And you just said if you use, what was it, 0.099, what was that?
0.99, I said.
If you use 0.99, you would still use the natural log of the n would just change, it wouldn't be 66.
That's correct, it'd be a bigger number. Yes, that's right. Okay, so that's what we have. Is that okay? That's what gives some kind of notion. You see, for each x, we get a convergence. And the n that we use, and when I wrote up that definition, the n that we use depends on the epsilon, how close you want to be. It depends on how close you want to be. But then it also depends on the x. That's what we're indicating. And that's why I wrote down n sub x, comma epsilon. Is that all right with everybody? And that's what we're talking about point-wise. In some sense, we're saying, hey, look, for a fixed x, the rate of conversion for this fixed x, where I am, is not the same as the rate of conversion for this fixed x. You know, the bigger you go out to the right, the, if you will, the bigger, the more terms of the sequence you have to go with. The same one doesn't work. But maybe you could get a collection of numbers, or a collection of functions, where the same n would work for all x's. And that's what uniform convergence has to do with. Is that okay? Okay, so this guy isn't uniform convergence. What is uniform convergence? I just want to highlight this other thing. I don't know if I ever had the camera on this part. Just in case this was to work over here. By concluding that the f sub n converges pointwise to 0 for x is between 0 and 1, and then a specific illustration of epsilon being 0.01 and x being 0.9. How far along in the sequence we have to go? Is that okay with everybody? Is it okay what I said? Okay, so this kind of example initiates that, well, we have to use a different n. Is there some way that we can use the same n, or what should those collections, what should that sequence be called? And so that's uniform. Okay, so definition. A sequence f sub n, and they're complex value functions. Okay, that's what we're working with, which include real value functions. Defined on a set E is said to converge uniformly to f, the function f, on E, if for each epsilon greater than 0, I'm going to stop for a second. I'm sorry if I'm going too slow, but I want to go a little slow. Ruby, everything all right?
Slow is so good. I just want you to understand that. This is great.
Slow may mean we stay a little longer.
Okay. That's okay.
Yeah, that's fine.
In the definition for point-wise, I said for each epsilon greater than 0 and each x in E. I'm not going to write down each x in E. I'm going to say for each epsilon, there exists a natural number n such that for all n bigger than or equal to this big N, f sub n of x minus f of x will be less than epsilon. And that's true for all x in E. So the all x in E comes later. And most mathematicians would say, in most cases, when we say for all or for each, we mean the same thing. But in these two definitions, we don't. In the convergence point-wise, we're saying for each x, there's this n. Okay? Here, we're saying, hey, there's this n that works for all the x's. One n works for them all. I feel like I'm talking about Lord of the Rings. One n to control them all. Okay, and that's exactly right. I'm glad if I said something wrong. Okay, I'd like to look at an example. And in some part with us doing this now, remember this is related to the homework. I asked a problem to show this is pointwise convergence. And to show that it's not uniform. There's one problem in homework is like this. Okay. Maybe I can get the Mountain Dew on tape. That'd be good. Okay. There you go. So as an example, let f sub n of x be the x sub n on, let's say, 0 to 1/2 in this way. Okay, not the 0 to 1, 0 to 1/2. Then the sequence of f sub n's converge uniformly on 0 to 1/2 to 0. Remember, I'm trying to look to get one n to control them all, not that the n would depend on x and epsilon. In terms of a picture, if this is a half, this is a half, and the first f sub 1 of x is just x to the first, that's y to x, that's just a straight line. And then the next guy, what's it going to look like? It's going to look like this, x squared, and its output value, draw it here, but its output value at 1/2 is 1/2 squared, which is a 4. And then, x to the third is going to be going up to get to 1/8 there at the end. Is that okay? And so forth. Okay? Now look, if you put some band, epsilon units, about 0, okay, you go epsilon units above and below. For uniform convergence, we want to find one n such that that whole function, that whole curve, is going to be within that band. Is that okay? Okay. And really the thing that makes this happen, and for us to prove it very easily, is there's one number in between 0 and 1/2 that for each function, that number raised to the n is bigger than every other number raised to the n. What number is that? I'm going to say it again. There's some number in between 0 and a half, such that f of that number, f sub n of that number, is bigger than or equal to f sub n of any other x in between 0 and a half. What's the maximum value? Where does it occur for each f sub n? What x value is the maximum value? At 1/2. So once I control how fast 1/2 goes to 0, I'm controlling them all. That's the idea. Is that okay? That's right. We good with that? Okay. So here's what I would do. Here's the way the proof would go. Proof. We let epsilon be greater than 0 be given. We need a natural number, n, such that for all n bigger than or equal to this big M, f sub n of x minus 0 will be less than epsilon for all x n 0 to 1/2. So I'm looking for this n. And I would say we want f sub n of x, again, is x sub n minus 0 to be less than epsilon. That is, we want x sub n to be less than epsilon. That's what I want for all n's bigger than a certain number. Is this okay? Yeah, I'm going too slow. Well, note, for all xn 0 to 1/2, x to the n is going to be less than or equal to 1/2 to the n. The 1/2 to the n is always the biggest number for each one of the functions. Is that okay? So if I want to get x to the n to be less than epsilon, it would be good enough to show 1/2 to the n is less than epsilon. Because once I get 1/2 to the n less than epsilon, I'm getting all the x sub n's to be less than epsilon. That's what I'm going to do. So here, note, I'll say, if we can get 1/2 to the n to be less than epsilon, we'd be done. Well, so we want 1/2 to the n to be less than epsilon. Well, that's the same problem we had before when we just had x to the n to be less than epsilon. So we want, it was n to be greater than ln of epsilon over ln of 1/2. That's the same work, okay? Just what we did before. Exactly the same thing we did before. How do I know that there's an n, a natural number bigger than this ln of epsilon over ln of 1/2? Because of the, what's its name? That's right. So choose big N, a natural number. Such that big N is bigger than ln of epsilon over ln of 1/2. Then, for all n bigger than that particular big N, we have x of n minus 0 inside absolute values be less than epsilon, and that's true for all x element of 0 to 1/2. So, f of n of x converges uniformly to 0. I'd like to do another example. But before I do, let me look at something that's from the homework. Look, problem 6 on your homework basically is a 3-point problem that's easy. Okay? We just have to write it up nicely. But problem 6 says, if f sub n converges uniformly on n, then f sub n converges pointwise on n. What is that saying? It's saying if there's one n that controls all the x's getting close to, all the f sub n's of x getting close to f of x, if there's one n that does it for all of them, then there's an n that does it for each. That's all that's being said. So we just have to write it nicely. Okay? But that's the idea. It's easy. Is that okay?
So what you're saying is just use the definition to try and say it.
Yeah, that's right. The definitions give us the answer. That's right. That's right. Okay, let's look at another quick example here. So if you're uniformly convergent, you are pointwise convergent. But the other way doesn't carry. Okay? You can be pointwise convergent but not uniform. Okay? So we saw an example of that. And here's what I'll say. Same type of situation. Let f sub n be f sub n of x be equal to x sub n on, let's say, from 0 to 1 open. Then f sub n, they converge pointwise to f of x equal to 0 on 0 to 1 open on the right, but not uniformly. Okay. So what I want to concentrate, the convergent pointwise, we did. Okay? It's with that ln of epsilon over ln of x. We already did it. Okay, the thing I want to concentrate on is the, why is it not pointwise? Okay, so how would I show that convergence is not, I'm sorry, I didn't say the right thing. How would I show the convergence is not uniform? Okay? Well, here's the way we would do it. What does it mean to be convergent uniform? That means you give me any epsilon, there exists this one n, such that for all little n bigger than this big N, the norm of f sub n of x minus, in this case 0, will be less than epsilon, and that's for all x in between, in this case, 0 to 1. Is that all right? So the opposite of that is that there exists this epsilon that's greater than 0, such that for all natural numbers, for all big N you could give me, there exists a little n bigger than that, and an x, such that f sub little n of x minus 0 in the norm is going to be bigger than or equal to. Is that okay? Epsilon. So here's what I'm going to do. I'm going to say, let epsilon be equal to 1/2. Okay? And I did this in the video lecture, I believe. Okay? I think I did this, but it went real fast. Okay. Let n be a natural number. So you give me, I give you a specific, there's a specific epsilon out there, so that no matter what big N you get, okay, you give me any of them, okay? So any natural number you give me, then I want to produce something bigger than this natural number now, such that, and an x, such that x to the nth power minus 0 is going to be bigger than 1/2. So we will produce an n bigger than big N such that, I should say, I should do this. I'm not sorry. Then for every n, hold it just a second. I'm going to take a second. I'm sorry. So I give it. We will produce an n bigger than big N such and x element from 0 to 1 such that f sub n of x minus 0 will be bigger than or equal to 1/2. Okay. All right, so here's what I'm thinking. If we look at if you will, we want to get bigger than or equal to 1/2. So let's look at the n plus 1, big N plus 1 root of 1/2. Big N plus 1. Let's talk about it. Just for a second, let's just look at it. When you take the square root of 1/2, anybody got a calculator? I know this. I see one right here. Go ahead. What's the square root of 1/2? What is this number?
1/32.
What decimal representation do you get? Yeah. Okay, you get 0.7. Okay, is that all right? And 0.7 is bigger than 1/2. You guys see that? But sandwiched in between 0 and 1, but bigger than 1/2. And what if you took, instead of the square root, what if you took let's try the 8th root. So here's what you do. You type in 1/2, raised to the 1 divided by 8. Okay? Raised to the quantity 1 divided by 8. N plus 1 is what it says. What'd you get?
0.9.
0.9 is what you got.
Almost 0.92.
Okay, so it went from the square root of 1/2 to being something like 0.7 to the 8th root of 1/2 being to 0.9. And the higher roots that we take of 1/2, the closer it gets to. Okay. So this number, I will say, is bigger than 1/2 raised to the nth power. Is that okay? Okay? And that's going to be bigger than 0, and it's still going to be less than 1. Is that all right? And the nth power, this guy, so this big N here, and this is going to be bigger. I should back this up. It's really going to be bigger than 1/2. Okay? That's what I got. Is that all right with everybody? And so here's what I claim. So the n plus 1 root of 1/2. It is a number in between 0 and 1. Just get close to 1. F of the nth plus 1 root of 1/2. Well, that's going to be, let's talk about the n plus 1 function of it. What's that going to be? So this is the f sub n plus 1 of the n plus 1 root of 1/2. That's right. So this is the n plus 1 root of 1/2 raised to the n plus 1. And what's that equal to? Okay. Is that okay with everybody? So really, if you want, you can change your epsilon just for a second. Let's just make it to a third. So, hey, can you make all the points be within a third unit of 0 for one n? Will one n do it? No. Because I can always find a point that's in between 0 and 1, and I'm saying it's the n plus 1 no matter what n you gave me, n plus 1 root of 1/2. Okay? That when I look at the n plus 1 function of that, evaluate that, I get 1/2, and that's going to be bigger than my epsilon, which is 1/3. Is that all right? Okay, I would like to draw a picture. Okay, so here's a picture. We're looking from 0 to 1. So it starts off, here's 1, and it looks like this. Let me bring this up. That's f sub 1, straight line. That's f sub 2. F sub 3. Is that okay? And so what's saying for non-uniform convergence, if we take a look at 1/3, okay? Epsilon equal 1/3. That means a band that's like here. I want to go far enough along the sequence such that the whole function and all the function from the nth spot on are within this band. And I'm telling you that's impossible because I can go far enough along closer to 1. Is that okay? Such that they're getting out of that band. And here's the exact details of it. Is that okay? That's what I'm saying. So it does not converge. This sequence does not converge uniformly. Because there's always some number, Shannon, that's popping out of that band that I have about 0, 1/3 0. In the function I'm not asking you, the sequence of functions that I'm asking you in the homework to show that aren't uniformly convergent. If you graph them, this is for problem number 7. If you graph them, you see, so I'm looking at problem 7 for a second. If you look at what x equal to 1 over n, you look at the functions, okay? When x equals to 1 over n, the output value for the nth function involved is n squared times 1 over n. That is n squared times 1 over n. N. And so I give you an epsilon. You say, well, can I get some number outside that epsilon? Well, you take a big N. If you take a big N, that n squared times 1 over n is going to be a big number. It's going to be outside epsilon units of 0. Okay? Is that okay with everybody? That's the idea. Has anybody graphed that sequence of functions? What do they look like, Shannon?
With the x-axis, they look like triangles.
They look like triangles. You're making triangles. They get higher, and they get their width gets they get less wide, and they get taller. That's what's happening. Is that okay with everybody? And they will converge pointwise to 0. I'm asking you to prove that, but they will not converge uniformly to 0 because there's always some point that's getting away from 0. Is that okay with everybody? Okay. So I wanted to talk about those problems and give you those definitions and examples to hopefully be helpful. Okay. I'd like to stop for a second and ask, does anybody have any questions about what we've done?
I think that's helped a lot with the difference between.
It's okay? Okay, I'm glad, and that's what I'm
But
trying
even
to do.
with the videos, I was kind of confused on it. I know we had talked to them too. So.
It's hard to understand it. It's hard to explain it in terms of, especially videos without people being here. And one of the things that I think is very frustrating in graduate school, and I didn't understand this as a graduate student most of my years, but essentially the professors are giving you material that maybe is missing some details that they're hopeful you can fill in so that they cover more. So they're worried about getting through a lot of material. And then they say, well, you could finish this off from here. But they're not showing all the details. And so we're expecting you guys to fill in those details. That makes it a little tough. Well, we talked about uniform convergence. And I'd like to do that Cauchy criterion for uniform convergence. Because I'm going to ask you to prove that. Okay? There's no ifs, doubts about it. That's going to be a question on your test. So I'd like to go over that with you. Before I do, though, I want to give everybody an opportunity again to say whether you have any questions or not. Anybody want to
Questions
ask?
on that or questions in general?
You can ask questions in general if you'd like.
I have a couple questions in general.
Okay.
When you're talking about, in the examples that you gave us about whether we have convergence or divergence,
For a series.
yeah, for a series. And you talked about the comparison test.
Yeah.
I'm a little confused. So if the P series converges,
So you're looking at a particular problem,
Yeah.
I think.
yeah, it's from the notes.
Okay.
Um,
But why don't you tell me what we're looking at?
Okay. The sum from n equals 1 to infinity of 1 over n minus 1/2 square root of n
N minus
1/2
1/2.
square root of n.
So we're looking at that particular problem. Okay, we want to know, does this converge or diverge? That's the question. Okay, so here, give me 1 second, Chris. 1 second. So the part of the comparison test we're going to use is this part. So here, the comparison test. Part B, it says if A sub n is less than or equal to B sub n is less than or equal to 0, and this is for n being greater than or equal to n sub naught, and if the series of the d sub n's diverges, then the series of the a sub n diverges. Okay. And so that's the problem you're asking me about for the notes, okay? And Chris, I didn't need to interrupt you. What I'm planning on doing is showing why this particular series diverges. Is that what you're looking to see?
Yeah.
Okay. Okay.
Which video was that covered in? 31? 21.
And it was example 7.
Okay, Chris, when I look at this particular series, when I look at this particular series, first of all, I'm going to use this part B of the comparison test. What I'm thinking is that my a sub n's are what I'm summing up in this particular problem. So here, I'm thinking a sub n is bigger than or equal to, and here's, a sub n, I'm going to let be 1 over n times, n minus 1/2 times square root. Okay? What I'm thinking is that is bigger than, or equal to. I'm going to put a little question mark about it. I think it's bigger than 1 over n. Okay? So what I'm doing is I'm going to compare the series of the 1 over n minus 1/2 times square root of n to the series 1 over n. Is that okay? Now, so I
Why
put
did
a
you
question
decide
mark.
to choose that series?
Say that again.
Why did you decide to choose 1 over n?
Okay,
That's one of my-
there's two reasons, okay? One is this guy looks a lot like this guy. If someone said, what dominates what's going on in a sub n's terms? I would say it's the n. The square root of n is still something important, but it's not as a big of power as into the first. And so that's what the more dominant quantity involved here. And then I also know what this series does. This series right here, what does it do, Chris? Do you know?
Diverges.
It diverges. Can you tell me why?
T series.
That's right. That's right. And so I know it diverges. Look, this is a bunch of positive numbers, 1 over n. We're adding them up, and to say that it diverges means it adds up and it goes beyond any finite number. It goes towards, the series goes towards infinity. Is that okay? Okay? That's what happens. And what we're thinking is if these terms right here are bigger than these terms, which sum up to be something going towards infinity, then these terms have got to sum up towards infinity and thus diverge. That's all right, Chris? That's the whole idea. So I told you why I picked what I did because it resembles the formula we had. I just got to show this. Well, here I'll say note. Note. N equals to n. Okay? And then, also, 1/2 times the square root of n is greater than 0. So n minus 1/2 times the square root of n. I've taken away something positive, Chris, from n. Is that okay? Okay? I've taken away something positive. So that guy isn't as big as n anymore. Is that all right? I've taken away a positive number from n. So it's not as big as n. Are we good with that? And then I'm going to divide, these are still positive numbers. I'm going to divide everything by n. Get n minus 1 over 2 times square root of n divided by n is less than or equal to 1. And now I'm going to divide everything by n minus 1/2 times square root of n. And so I get the inequality, even though I've written it kind of with the subject being changed, you know, that I wanted. Is that okay? And so that's the reason I can say by the comparison test that series diverges.
What if you had n minus 1, sorry, n plus 1/2 the square root of n?
So n one over n plus.
Just check the one.
Yeah, just change minus to plus.
Okay. Okay, that's all right? All right. So here it's a little bit more difficult. Okay? Here's a little bit more difficult. But what I'm going to do is I'm going to say, okay, look, so is this something to worry about? I'm still thinking that it diverges. Okay? But what I'm thinking is that maybe I'll do this. Note, I got n plus 1/2 times square root of n. Okay? So I'm looking at this guy. And this is the same thing as the square root of n squared times square root of n. Let me not write it. Plus 1/2 times square root of n. That's the same thing, okay? I'm looking at that. So this is just what I'm looking at right now. And I can factor out a square root of n. And then this is going to be the square root of n plus 1/2. Okay? Yeah, that's what I got. Okay, so I know that those two are the same. All right. Okay. Now, the square root of n plus 1/2 is bigger than 1/2. So this is, I'm going to say is, I'd like for it to be less than something. Okay. So because I'm going to divide. So I'd like for this to be, if you will, we end up having a less than quantity is what we want. Okay. So less than. So here for a second, maybe I can replace the 1/2 by something that's bigger than n. So what about the square root of n? No, the square root of n is going to be bigger than or equal to 1/2. It's going to be bigger than 1/2 for every n. Is that okay? Okay? I mean, square root of 1 is, square root of 2 is, okay. So I'm going to say, hey, this is going to be less than the square root of n times the square root of n plus the square root of n. Is that okay? So I just replaced the 1/2 by something bigger than n, which was the square root of n. Okay? All right, what's this? This is equal to the square root of n times 2 times the square root of n. Okay? And so this is equal to 2 times n. Is that all right? Okay, so here's what I got. So present, it took me a second to maybe get an inequality I wanted. Are we okay with what's done? I'm asking. I'm not trying to be nosy. I'm just asking.
No, this is why I had a problem with this one, because we wouldn't have the less than right away. That's why I was.
Okay, so I've got square root of n, and square root of n plus 1/2 is going to be less than or equal to 2 over n. So this says 1 over 2n is going to be less than or equal to 1 over, here this is n plus 1/2 times square root of n. Okay? Now, this series, what does it do, Chris? I mean, you can pull out the 1/2. Is that okay? And then you're just left with the sum of the, and we know it. That's right. Okay. So it diverges. So by the comparison test, this sum diverges. So we had to be a little bit creative in terms of what to compare it to. I don't believe that, I tried to stay away from some of that creativity type problems, even though there are things we can do. Okay? And so for the homework, the problem that I asked you was a comparison test. You don't have to be that creative.
Well, that's why when I was looking at this comparison test one on the notes, I was like, well, what happens when it's not less than?
Yeah.
How do you deal with it then?
Yeah, that if you just pull away this guy. Yeah, and so we have to try to rewrite it and compare it to something. If it diverges, compare it to something, where the positive terms involved. Compare it to something that is divergent, that is less than. We just have to be creative sometimes. It's okay what I said? Okay. Would anybody else like to ask something? Oh, I didn't hear it, isn't it? It is to me. Go ahead, Chris.
When you're talking about radius of convergence of a power series,
Yes, sir.
I had a hard time understanding some of those examples after I started looking back at them again.
Okay.
I understood, when I looked at the theorem that preceded the examples, I understood how we got to a certain point, but then I didn't understand how we got to that conclusion.
Okay. Well, there's one thing that I'd like to do. We've spent about an hour and 10 minutes in this room. The library closes at 5. Why don't we head back? I wanted to tape some of it for the people who missed. Why don't we say, well, that's all we can tape here, and we'll just go back to our room, 4:50, and we'll finish off about another hour, something like that, a little less than that, for the rest of the questions. And I do want to go over that code sheet, criterion for convergence. But Chris, we'll go ahead and answer your question, okay? Or look at what you want to look at.